Hey everybody, sorry about that abrupt ending there. My laptop got disconnected from my iPad somehow, and I don't know how to edit videos, so I don't know how to splice them together. So anyway, I didn't mean to cut it off like that. Just to wrap up this second example, what I was trying to say at the end there was just that there are two ways to do it. You, of course, pick your favorite. You don't do both. So on this last one here, I myself am partial to doing it the first way, doing the indefinite integral first and then coming back to the bounds later. That for me, that's sort of conceptually cleaner. Okay, so here's just one last little practice with u substitutions, secant squared theta times tangent of theta. So I'm first going to think about this. I'm going to think about the indefinite integral secant squared theta d theta, tangent theta d theta, and then put the bounds in at the end. So to use a u substitution here, we have to look for a function whose derivative is also there being multiplied. And there are a few things you can try here, but tangent seems like the most natural choice because the derivative of tangent is secant squared. So therefore du is secant squared theta d theta. So we get a lot of sort of absorption here. The complexity of the integral dies down quite a bit. Secant squared d theta gets all absorbed inside the du, and then the u just eats that tangent. So I end up just writing down just u du. And that's a much simpler integral, of course. And so now to integrate that, it's just a matter of doing the backwards power rule. So this is u squared over 2 plus c. So back in theta language, this would be tangent squared theta over 2 plus c. And there you go. So as we've seen multiple times now, right, an obnoxious looking integral, right, trying to think about a function whose derivative is secant squared times tangent is kind of obnoxious. So you take this sort of more complicated integral, you change the language, in this case changing from thetas to u's, and get yourself a much simpler integral, right? This integral u du, that's just a matter of doing the power rule backwards. That's all right. So now I have to come back and put the bounds in. So I got to do 0 from pi to pi over 4, secant squared theta tangent theta. That is tangent squared theta over 2. I can drop the plus c now because now I'm in definite integral land, 0 to pi over 4. Okay, so now we just have to evaluate tangent pi over 4 quantity squared over 2, and then subtract off tangent of 0 squared over 2. So this, of course, depends on if you remember what these tangent values are. Tangent of pi over 4 is 1. Tangent of 0 is 0, so you end up with just a half. Okay, so again, all the work as I've written it is the way you'd want to show your work. Again, making no false statements or anything like that. And again, just notice how nice this technique is. Again, you're starting with an integral that looks like it's going to be difficult to handle. You know, like how am I supposed to think of a function whose derivative is secant squared theta times tangent of theta? And if like the chain rule is just not in your bones, you know, it can be hard to spot that chain rule that showed up there. Differentiating tangent squared over 2, right, differentiating this guy here, does indeed involve a chain rule because you got to deal with the squared, right? Anyway, whoops. So it's just a nice technique. It reduces the complexity of integrals down quite a bit to leave you with just this nice sort of integral here that you can handle without too much trouble. And then again, with u substitutions with definite integrals, for me anyway, I then come back at the end and plug the bounds in as a last step. Okay, so hopefully this was of some use to you, this video. Hopefully it's now clear how you do both indefinite and definite integrals with u substitution. And next time we'll move on to section 6.1.